Hello, my name is Oren Minsk. I'm a sophomore studying mechanical engineering here at Penn. For my final project, I decided to create a toolbox of Home-Brew linear algebra functions that a user can interact with through an app. I knew I wanted to do something where I could apply what I had learned in another class to this final project, and I thought linear algebra has a lot of algorithms to determine certain characteristics of matrices that I could apply to MATLAB. So let's run the start file to open up my app. Let's bring it up here. So as you can see, we have an input. We have a bunch of input boxes where a user can enter a matrix of their choosing. You can see here that we can adjust the size of the matrix to make it any dimension up to 4 by 4 that the user wants to. And you can see that as I'm changing these values, changing the dimensions of the matrix, some of these buttons disappear. And the reason for that is some of these buttons correspond to functions that are only defined for square matrices, which are all of these ones on the right. So when I don't have a square matrix, say a 4 by 3 matrix, these buttons disappear because otherwise the function would try and operate on a matrix for which it isn't defined. But then when I bring it back down to a square matrix, say 3 by 3, those buttons are going to reappear. So let's test out the capabilities of this program. So let's take a 4 by 4 matrix. Let's say 1, 2, 2, 1. Next, we'll say -3. 0 is fine there. 2, 3. You can say 0, 1. 0, 1, sure. And we can say -2, 2, -2, and we can leave that as 0. So let's calculate the determinant as 32. We can calculate the real eigenvalues. And we can calculate the trace in the matrix. We can calculate the kernel of the matrix. We see that the kernel is just the 0 vector, and that makes sense because a non-zero determinant means that there is no kernel. I'm going to go to Wolfram Alpha right now, and we can check to see how accurate these numbers are. So we can plug in the matrix 1. We said 2, 2, 1, -3, 0, 2, 3, 0, 1, 0, 1, and -2, 2, -2, 0. And it will give us, so we got the determinant as 2, we got the trace as 1, and we can see here 2 of the eigenvalues are complex and 2 of the ones are real, -1 and -2.3018. Look at what we got -2.3019 and 1, so pretty close. Let's try one more matrix. Say 2, 0, 0, 1, make it a -1, -3, 0, so let's make that 0, and say 1, make that a -1, and say that is 0, this is 1, that's -2, and say this is 4. So let's do this again, calculate the real eigenvalues. There they are, calculate the trace. Can calculate the determinant. Calculate the kernel again, it's going to be 0 again. And we can check these as well really quickly. Let's go 2, 0, 0, -1. So -3, 0, 2. You said this is 0. So this is 1. This is -1. And then we had 0, 1, -2, and 4. So you can see that all of these eigenvalues that Wolfram Alpha found are the same exact ones that we found here, and we see the determinant found as -7, we found -7. Another cool thing is we can just replace this matrix with its transpose, like this, and it flips them across the diagonal. You can also see this for like a smaller matrix. So let's say we have the matrix 1, 2, 3, 4, and let's say we have -2 and 1. So one thing we can do is replace with the transpose, and it'll flip the dimensions, and we can calculate the kernel of the matrix. So we can see that these are the two vectors, where if we multiply these vectors by that matrix, it'll give us 0. So let's go back to the MATLAB editor, and we can look a bit at some of the files. So each of these files corresponds to a different one of the functions. Some of them are a lot more complex than the others. Some of them are a lot more simple, like this transpose one, the trace one. The row reduced echelon form one is a bit more complicated. The function I want to spend the most time talking about in this video is the eigenvalue function. And the reason for that is because I needed to spend a lot of time optimizing it, and it was one of the more challenging ones to build. So originally this function was only able to detect eigenvalues between -5 and 5, and it took upwards of 45 seconds to run, but by replacing loops with array operations as well as some other techniques, I was able to cut the runtime down to around 3 seconds, which is much more acceptable for a GUI, and it can now detect eigenvalues between -15 and 15. And obviously not every matrix is going to have all of its eigenvalues fall within that range, so I wanted to experiment and gain some data about how many matrices have eigenvalues that I would miss. So what I did is I wrote this script which basically generates random matrices that have a max or a minimum entry and have a certain dimension. And what this does is that it'll generate 1,000 of these random matrices, and it will calculate the eigenvalues using MATLAB's built-in eigenvalue function. And then it'll see how many of them are outside the range of -15 to 15, and then using that information, it tells me what percent of those matrices I would miss, or what percent of those matrices have eigenvalues that I would miss in, like were I to use my function on those matrices. And I ran this a lot of times to get to see what the most consistent answer was. And what I found was that for 3x3 and 4x4 matrices with entries between -5 and 5, that number is consistently 0% of matrices whose eigenvalues I would miss. For 3x3 matrices with entries between -6 and 6, that number is also consistently 0. So just to test that, so we see n is 6, which means that the max and min entries are going to be -6 and 6, and s is the side length, so that'll be 3. And if we run this, we see percent missed is 0, and then it pops up with the quote plot too. Let's close that. We'll just minimize it for now. So that's to say that for almost every matrix that a student at Penn might encounter in a linear algebra course, all real eigenvalues can be found using my function. But not for all matrices ever, right? So for 4x4 matrices with entries between -6 and 6, that number was consistently around 4% of matrices. So we can see that if we do, I'll plug this in, plug in 4, percent miss is like 4.1, right? And I'm just going to close this. This is just a plot of the max eigenvalue versus the max entry in the matrix. So this is the max entry from 3.5 to 6, and then the max eigenvalues. Almost all of them are below 15, but not quite all of them. So basically larger numbers tend to lend themselves to larger eigenvalues. So the smaller the numbers in the matrix, the more likely the matrix's eigenvalues are to be found by my function. One thing that I tried to add to my app that I was not able to figure out was the multiplicity of each eigenvalue. So for a given matrix, it may have two eigenvalues that actually have the same value, but my function is not able to detect that the multiplicity is not 1. I had tried thinking of a number of ways to find the multiplicity of eigenvalues, but I was not able to come up with one in a way where I could write a function for that algorithm. One thought I had was that if I knew a matrix is 4x4 and it has two real eigenvalues, that each of those eigenvalues must be multiplicity 2. But that actually ended up not being true because that matrix may have complex eigenvalues that my function is not able to find. I had thought of using some other linear algebra techniques, other than kind of this main one of using the characteristic polynomial, but there wasn't enough documentation online for me to gain a solid enough understanding of the method to use it in an algorithm or a function. So there are limitations in my app, although it does work for a large number of matrices, and most matrices that would be relevant to students in a Penn linear algebra class. Thank you so much, and this has been my final project.